Hello, this is Adam Wu. Let's take a look at the drawing annotation. In this drawing, the flatness of the lower surface is 0.2, while the profile of the upper surface is 0.1. In other words, the tolerance of the datum itself is larger than the profile tolerance. So the question we are going to discuss today is there anything incorrect about specifying it this way? Let's first understand this from a theoretical perspective. This is the actual part. Its lower surface is certainly not perfect. In the microscopic world, it is machined into a curved surface like this. Note that this surface itself is not the datum. It is called the datum feature. And it definitely has flatness error. In fact, today's topic should more precisely be stated as: can the tolerance of a datum feature be larger than other tolerances? Now, this surface is not datum A, because datum A must be a theoretically perfect plane. So, where is datum A? According to default rules in the standards, the datum is established by an external contacting plane. This blue plane is what we call datum A. Let's take a look at a 3D view. The actual lower surface of this green part is the datum feature. We then apply an ideal plane to contact it externally, and that is how we obtain this blue datum A. Now let's take a look at the profile tolerance zone. It is the region between two parallel planes. This region is perfectly parallel to datum A, with a width of 0.1 and located at an exact distance of 30 from datum A. This red region represents the profile tolerance zone. Let's explain this using a 3D view. This is the actual part, and this is the datum A. The tolerance zone is the region between two parallel planes with a width of 0.1. The tolerance zone is located at a distance of 30 from the datum A. Finally, the requirement is that as long as the actual measured feature lies within the tolerance zone, the profile tolerance is considered acceptable. At this point, after explaining the concepts and the relationships of the datum feature, datum plane, and the tolerance zone, let's take a look at the confusion that engineers often have. Here, since the flatness of the datum feature is 0.2, it means that the maximum distance between the peaks and valleys of the actual lower surface is 0.2. Many engineers therefore assume that the datum could randomly shift within this 0.2 range. Furthermore, because the tolerance zone must maintain a theoretically exact parallelism and a theoretically exact distance of 30 from datum A, they believe that the tolerance zone could also randomly move up and down within this 0.2 range. At this point, it appears that the measured feature would be non-conforming. It is almost like trying to hit a moving target in shooting. It becomes very difficult to satisfy. Based on this reasoning, many engineers conclude that since the datum feature has a flatness of 0.2, which is larger than the profile tolerance of 0.1 on the upper surface, this specification must be incorrect. So now the question is this reasoning correct? For a finished part, can the datum really shift randomly within 0.2 flatlist range? And can the tolerance zone itself also move randomly within that same 0.2 range? The key point here lies in how the datum is established. As we just discussed, the datum is created by external tangency, which implies two things. First, the datum must lie outside the material. It is determined by the highest point of the datum feature, that is the actual lower surface, and it cannot penetrate into the material. Second, once the datum is established, its position and orientation relative to the actual part are fixed, with no other possibilities. In other words, the datum cannot move up and down arbitrarily. This is why we say that datum has a unique orientation and position relative to the actual part. Now, the tolerance zone above must maintain a theoretically exact parallelism with the datum, as well as a theoretically exact distance of 30. Therefore, the tolerance zone has a unique position and orientation relative to the datum. And since the datum itself has a unique position and orientation relative to the part, it follows that the tolerance zone also has a unique position and orientation relative to the actual part. From a manufacturing or inspection perspective, the requirement of the profile tolerance is therefore well defined. It is not a target that can move arbitrarily. According to the latest standards, whether ISO or ASME, the method for establishing the datum is clearly defined as an external least squares fitting. When this mathematical method is applied, the resulting datum plane has a unique position and orientation relative to the part. In other words, the tolerance zone also has a unique position and orientation relative to the part. The target is not moving. So, the key takeaway of this video is, even if the flatlist tolerance is large and the profile tolerance is small, there is no theoretical error in this specification because the two are not directly related. Does that make sense? Finally, I'd like to point out that when I say there's no issue in theory, I mean there is no problem from a logical standpoint. However, is this type of specification good practice in reality? Does it have any side effects? You are welcome to share your thoughts in the comments. Follow me to keep improving with every episode.